This presentation is continuing with Module 4, Exploring Distributions. This is Topic 13 in the workbook on measures of dispersion. And we're going to learn 3 measures of dispersion today: mean absolute deviation, variance, and standard deviation. And we're going to talk about these first as population parameters, and then we'll talk about the sample statistics that you could use to estimate these. This topic 13 in the workbook starts on page 114 in the August 2020 edition. Okay. So we've already had a couple of measures of dispersion. In previous videos, we've talked about the range. You take the biggest x value and you subtract the smallest x value, and it's a way of finding out how spread out is your data, just what's the distance from the smallest to the largest. And if you're talking about a population, I'll be putting this little subscript, POP, there to distinguish this from a sample statistic, which would be the same thing, but when you don't have access to the entire population and you're just finding the range of your sample. This range is not a robust statistic because, well, it really, you know, if you get a sample of, I don't know, 30 randomly selected US citizens and you get the range of their income, it's not going to be anywhere close to the range in the whole population, because if you don't get Bill Gates or Warren Buffett in your sample, you know, the range is not going to be anywhere close to the population parameter. So samples are not very useful. So that's a case where the sample statistic, the sample range, is not very good at estimating the population parameter. Okay. But much better than that, we've talked about the interquartile range, the IQR, in a previous video. Find how far is it across the middle 50% of the population. So you take the 50% of the people closest to the middle, and how far is it across them? The third quartile minus the first quartile is how you do that. Much more robust. But this presentation today is about 3 new measures of dispersion. These are going to be more robust than the range, but less robust than the IQR. And the one we're really after is this one, the population standard deviation. But for teaching reasons, it's just easier to build up to that. And so I'm actually going to start with this population mean absolute deviation because it's easy to understand, and it's almost the same thing as the standard deviation. The numbers come out pretty close most of the time. So it'll give you a concept for what it is we're talking about. Okay. So I'm going to stop the video of me talking, and I'm going to go over here to the piece of paper, and I'm just going to write on the piece of paper for a while. Okay, so so this one, the population mean absolute deviation. So what we're doing with this is we're finding the average distance away from the mean. So let's consider, well, maybe we have this little population. So for example, maybe Maybe the population is the set of all the students in our class. Now, that's not really a good example of a population, because usually your population would have millions of people in it. But I'm just doing this so we can visualize it easily. Okay, and what I want to calculate, this measure of how spread out the data is. Let's see, we need a variable. So I'm going to use the height as the variable. Okay. So this variable x, it's a function. You give it a student, it gives you back the height of that student. And you can do it with any of the students or all of them. Okay, now, what I want to do is find out how far from average is the average student. Okay, so like if we were in the classroom, what I would do is just point to some students and say, okay, maybe you're 2 inches below average, and you're 2 inches above average, and you're 3 inches below and 3 inches above. We make all those positive numbers, just distances, and average out the average distance away from average. Okay, so my first step would be I'd have to work out the average. So I'm going to find the population mean. So I make the sum of the x values for all the students and divide by how many students there are in our population. That's the population mean. I'm using the Greek letter mu to stand for that. So what I'm going to do is I'm going to find out how far from average is student number 1. So I just go down the row and I take the first students height, and I subtract it from the average or population mean height. And if I get a negative number, I make it positive. So I've got the absolute values on there to make all the positive distances. And I want to get the average distance from average. So I add up all the distances and divide by how many of them there are. So take 1 over n times the sum of all those distances. And so that's my mean, or my average absolute deviation. How far does each individual deviate from the mean? And then we take the mean of that. So the mean absolute deviation, I'll call that MAD. For the population. Okay. So that would be just like the ideal measure of dispersion. How spread out is the data? How spread out is the population? Well, is the average distance away from the middle. That would totally make sense. There's a problem with it. Because of the absolute value, it's hard to work with, and it's hard to prove theorems about. And so there's this closely related thing, the variance, which is just easier to work with, and it pops up in something we're going to learn about a little later in the semester, the central limit theorem. It's really because of that theorem that the variance is important. So it's starting with this mean absolute deviation idea and just tweaking it a little bit to get rid of the absolute value, to make something easier to work with for, Gauss could work with it easier for proving his theorem. And then the variance turns out to have a lot of connections to other parts of math as well. So Gauss kind of got lucky that way. So I'm going to move off of the mean absolute deviation, and what I do in the classroom when we're meeting in person is I just ask for people to put up their hand and ask, do you have any idea? We're putting the absolute value on there because we want all these distances to be positive. If we left it off, we'd just get 0 every time, because the xi is bigger than mu just as often as it's smaller than mu. You can do the algebra, but it comes out to be 0 every time, and so that's why the absolute value is there, to make a distance without negatives. Now, if I asked you, can you come up with another way to just get rid of the negatives? Every year when I do this, after a few minutes, somebody's going to put their hands up and they're going to say, well, what is it you can do to a number? The result's always going to come out positive. And they say, well, you can square it. If you take a number times itself. like -3 times -3 comes out +9. If you square a number, it makes it positive. And so that's the idea. Instead of doing the absolute value, you do the squares. So our population variance is real easy to write down. So I'm adding up the squares of the distances from average and dividing by how many of them there are. The average squared. You can also call this the mean squared deviation. So without the summation sign, it's just that. It's just adding those differences up, adding the squares, and then divide by how many. Okay. So that's pretty good. But I want something that's more like what I had a second ago. See, this thing, when I subtract, I get how tall you are minus the mean, and it's a number of inches, and I average this, I get a number of inches. And it's easy to understand because you can say, okay, on average, people are 2 inches different from the average. Okay. But this one over here, with the variance, I subtract and I get inches, and then I square it, I get square inches. And so, I ask you, how spread out is the data? And you say, so many square inches. It doesn't sound right. It doesn't make as much sense. And these numbers might be a lot bigger than what I would have gotten if I had just done the absolute value. When I do all that squaring, depending what size the numbers are, they may be getting bigger. So the next question I usually ask the class when we're meeting in person is, well, so if you wanted to bring it back down closer to where it would have been if I had not done the squaring, if it had been like the absolute value, what could you do to bring it back down? And somebody always says, well, take the square root, and sure. So that's your population standard deviation. We're going to use this Greek letter sigma. I don't know, you see our summation sign over here, that was the capital sigma, that's Greek. And so that one is just an initial for the word sum. It stands for summation. This, I suppose, this is a Greek S, lowercase. I think it stands for standard. Okay. So that's just the square root of the variance. So it's the square root of 1 over n times the sum of the squared differences between the data and the population mean. Okay, now I need to talk about how you estimate this. Because my story about the population was just the students in our classroom, it's not very realistic. Usually the population is much larger, and you're trying to get an estimate just based on a little sample. So I need to talk about the sample variance. And then I'll take the square root of that to get the sample standard deviation. Now, so if you don't have access to the whole population, you don't know mu. What's the next best thing? So really, I'm looking at this formula up here without the square root right now. I want to do that, but where I don't know the mu, so I don't have access to the whole population, that I can estimate the mu using the sample mean. So I'm adding up how far everyone is away from the mean. It's just the sample mean. And I don't have the big N. I don't have the millions in the population. I only have a little n, the sample size. So maybe instead of using 300 million US citizens, we're using 100 randomly selected US citizens. The little n would be the 100. Okay. And then you would think, so instead of dividing by the big N, I would just divide by the little n. You would think that, and in fact people did think that for quite a few years, until they realized it's a mistake, a very small mistake, that it would make the answer, the variance, come out a little bit less than it should. So I'm going to divide by something. And before I tell you what, I want to talk about bias. Why these differences, xi minus x bar, tend to be just a little bit smaller than xi minus mu. Why is that? Well, let me just ask you. Say we were talking about incomes of people. Do you think your income is more likely to be near the class average income or near the national average income? Maybe the people in the class are more like you. And maybe we don't have Bill Gates in the class. And so maybe your income's closer to the classroom average than the national average. But here's the thing. What do I mean by an unbiased statistic? What I mean is, if I were to get lots of different samples, okay, it's our classroom today, but tomorrow I get 30 randomly selected US citizens, randomly selected, scattered from all over, 30 of them. The day after that, I get another different sample, and I keep working out the sample variance over and over again. At least it's an unbiased estimator for the population variance if, on average, from all those different samples I might get a different sample variance every time you get a different sample, but at least maybe they should all average out to the population variance. If they do, then you're using an unbiased estimator. Well, that population mean, that mu, is just fixed. There's just one average for all the people in the United States. But every time you get a new sample, you get the sample mean, this x bar moves around. And it moves around so as to sit right in the middle of the people who make up your sample. So like if our sample was the people in our classroom, the sample mean would sit right in the middle of all of us. So we'd all be pretty close to it, because it is adjusted to be right in the middle of us. And then I get a different sample tomorrow, and the x bar moves to be close to the middle of those people. So all those differences will still tend to be a little bit small. That's not happening with the population mean. It does not bounce around. It's just one fixed number. So when I replace the mu that holds still with a sigma that moves around to be close to the xi's, it creates bias, and it makes this thing tend to be too small. And that's why if we just divide by an n here, without any adjustment, our sample variance on average is less than the population variance. Now, it's just an algebra problem, but it's a hard one, and I'm not going to do it. You'd go to sleep, and I'd probably mess up along the way. But it's just algebra. If you divide by n minus 1, instead of the n, then you have an unbiased estimator. You divide by a little bit less, so it makes this a little bit bigger, and it turns out to be just enough bigger so that on average, if you consider all possible samples, the average sample variance is the same as the population variance over all possible samples. Now, any particular one sample you get one day, it's not going to be exactly the same. Some will be bigger and some will be smaller, but it averages out right, and that's what I mean by unbiased. So that's the sample variance. And then to get the standard deviation, it's just the square root of the variance, same way it was before. So if you're going to work this out by hand, straight from this definition formula, so all three of these are the definition formulas for the standard deviation and variance. So on a test, I might ask you for this definition or this definition. And if you were going to work out the sample standard deviations, working straight from this definition, you'd have to do all these subtract. You'd have to get all these differences, subtract everybody minus the mean individually, square all those, then add them up, then divide by n minus 1, then take the square root. Now, in a separate video, I'm going to work on some shortcut formulas that can reduce the amount of arithmetic. I'm going to simplify these things a little bit to reduce the amount of arithmetic. And then in another video, I'm going to show you the Excel functions to do this for you, so you won't really have to do very much arithmetic. But you want to understand what it is that Excel is doing for you. So that's all for this topic.